Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 27 from the course, but make sure you have watched the previous ones before viewing this one. Well, this is going to be the last lecture as far as the theory for the subject course is concerned, but we will be taking one more lecture to do the numericals based on the electronic configuration that we are going to learn in this lecture. So moving on from the various energies of the orbitals and then the rules for filling these orbitals, today lecture is going to apply those concepts and fill in the electronic configuration of various elements. So let us learn how we write these electronic configurations. Well, why do we need first of all to write the electronic configuration is what you should understand, because when we know the exact electronic configuration of an element, this is going to give you us an assessment about the relative arrangement of the electrons in an atom, and this is going to help in predicting the properties of these elements. Okay, so the properties of the element, they are going to be based on the electronic configuration, which you will be able to appreciate when you study the next course, that is the periodic table and periodic properties of elements, right? So there you will understand that this electronic configuration that you are going to learn is going to be helpful for predicting the properties of these elements. So that is why we want to learn to write them. And now, how will we write them? Well, we will go by the rules for filling of the orbitals, and we can write the electronic configuration. For example, we have fluorine, which has atomic number 9. So the electronic configuration is going to be what? First, we are going to start the filling of orbitals according to their increasing energies. So the first orbital, which has the least energy, is the 1s orbital. And according to the Pauli's exclusion principle, we have to fill 2 electrons into it. So we have filled 2 electrons, right? So atomic number 9 means we have 9 electrons for fluorine. First 2 electrons go into 1s. Next 2 electrons, they are going into 2s. Done with 4, we have 5 left. 5 left, they have to go into the 2p orbitals. And for the 2p orbitals, how are you going to fill them? First, you will fill all the 3 orbitals singly. First 2px, 2py, 2pz. Then you will be left again with 2 electrons. So this means that you have to put the second electron into 2px, making it 2px2. Then the remaining 1 electron goes into 2py, making it 2py2, and 1 left again in 2pz. Okay, so this makes the electronic configuration of fluorine as 1s2, 2s2, 2px2, 2py2, and 2pz1. Right? And this is how we are going to represent the spin of these electrons. So you can see the spin of the electrons in 1s, 2s, and 2px, 2py, and 2pz. Right? Now, there are many ways in which we can represent the electronic configuration. We will be taking iron as an example with the atomic number 26. So 26 is the atomic number. So this means it has 26 electrons. We have to represent the electronic configuration for this 26 electrons. So filling in the relative energies according to the AUFBAU principle, we have 1s2, 2s2, 2p6. Then we have filled up here till 10. Okay, then we go to 3s2, 3p6, filling up 18, and then 4s2, right? Because 4s has less energy than 3d, so 4s is being filled first, and then the remaining 6 electrons, they go into the d orbitals. So this is how we have written according to the way we are filling the electrons in the orbitals according to increasing energy. Next, we can also write this representation of the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. So this representation is also not wrong. right? So this is also correct that we have put all the 3D electrons or in the various subshells together over here. And then we can also represent this configuration as the first we will write the nearest noble gas. The nearest noble gas, that means before the atomic number 26 is argon, which has atomic number 18. So we have written argon in a bracket. Okay, so this means up till argon, this is the configuration, and after argon what is being left is 4s2 and 3d6. So whenever you have to write the electronic configuration and we do not want to write such lengthy notations, what we do is the noble gas which is coming before the element that we have to represent, we will write this symbol in the bracket, and then we will continue for the valence shell, and if there are the 3D electrons like in this case, we will write that configuration after that. Okay. So the information which is conveyed to us by this electronic configuration that you can understand is, so this is the innermost orbit 1s2. Then we have the outermost orbit, right? Outermost orbit is called as the valence shell, or it is also called as the ultimate shell, which has the highest value of n. The highest value of n is 4. So the next lesser value is going to be n minus 1. Okay. So if this is n, this orbit which has n equal to 3, this is called as the penultimate shell. And then we have n minus 2 shell being called as the anti-penultimate shell. Okay, so you have to remember the valence shell, the penultimate shell is n minus 1, and anti-penultimate shell is n minus 2. Okay, and then the spin of the electrons, as I told you, this can be represented along with the electronic configuration. So we have the electronic configuration. Generally, we represent the valence shell. Right, the rest of the things we will not write, we will be writing the valence shell configuration. Okay, so the last shell, and if like fourth shell is going to be complete after the filling of the 3d6. So we write it 4s, and then we write the 3d6 electrons also, where the last electrons they are entering in. Now we are going to see the electronic configuration of various elements. For example, first of all, we will be starting with hydrogen. So hydrogen atomic number is 1. The configuration is going to be 1s1. Then we have helium atomic number 2. The configuration is going to be 1s2. Right? The second electron also going into the same 1s orbital. Then we move on to lithium 3. So now the second shell will start because the first shell is complete with 2 electrons. So the second shell, this is going to have how many subshells? It is going to have S and P subshells. So from the atomic number 3, we'll be starting the filling of the second principal quantum number. Okay. So we have 1s2, 2s1. Next, we have beryllium. It is going to be 1s2, 2s2. Then we have boron, with this going to be 1s2, 2s2, 2p1. So we are filling 1 electron with increase of atomic number by 1. We have carbon, it is going to be 1s2, 2s2, 2p2. And I hope will remember that this 2p2, this is not going into one orbital, but this will be going into different orbitals, 2px1, 2py1. Then we have nitrogen, 1s2, 2s2, 2p3. Oxygen having 1s2, 2s2, 2p4, fluorine having 1s2, 2s2, 2p5, and neon, the noble gas, where the electronic configuration for the second shell is complete. So this is 1s2, 2s2, 2p6. So for the next element, that is sodium, you can write the electronic configuration as 1s2, 2s2, 2p6, 3s1, or you can even write neon in the bracket as I told you for argon, and then after that you just write simply 3s1 rather than writing the whole long electronic configuration. So magnesium is going to be neon with the 3s2, or you can write it as 1s2, 2s2, 2p6, 3s2. Next we have aluminium. So this is going to be 3s2 3p1, silicon 3s2 3p2, phosphorus 3s2 3p3, sulfur 3s2 3p4, chlorine is going to be 3s2 3p5, and argon is going to be 3s2 3p6. So this is the next noble gas configuration where we have the fully filled third shell. Okay, the 3d electrons we are not filling in here because they have energy greater than 4s. So there the filling is going to start after we have finished the 4s orbital. So for potassium, the next electron after 3p6 goes into 4s1 and not 3d. Okay, so remember this. This is where we are applying the rules that we learned. So potassium is going to be 4s1. Then we have calcium is 4s2. Now the filling of 4s orbital is complete, and 3d electrons, they are going to have lesser energy than 4p. So we will now be filling the 3d orbitals. So scandium is 3d1, titanium is 3d2, vanadium is 3d3, and chromium is 3d4, and manganese is 3d5. Now why have I written this in red color is what we have to explain further on the next slide. Okay, so this chromium configuration, this is going to be an exception again to the AUFBAU principle, because this is going to be actually an application of the Hund's rule of maximum multiplicity, that we know that the fully filled and the half filled orbitals, they are more stable. So the electronic configuration of chromium, which should have been 4s2 3d4, is wrong, because here we have an incomplete filled d orbital. What we do is that 4s and 3d, they do not have much of energy difference. So what happens is that one electron from 4s, it goes into the 3d vacant orbital. Okay, so this makes the whole of 4s and 3d half filled, and half filled configuration is more stable. Hence this is the right configuration and not this one. Alright, similarly when you will go further up till copper, so copper has atomic number 29. The configuration for which is going to be, as according to the AUFBAU principle, you will move is 4s2 3d9. But again, this one orbital is incomplete, right? So what happens over here is that the 4s1 electrons, this goes into the 3d and this fills the inner shell completely. So this makes the configuration much more stable, much more symmetrical, as you can see. So that is why this is the right way to write the electronic configuration for copper. And these two, the configuration of chromium, of copper, this is frequently asked in the examination because of its exceptional nature. So I hope this is clear that for chromium, you are not going to write 4s2 3d4. You are going to write 4s1 3d5 because the half-filled orbitals, they are more stable. And similarly, copper is going to be 4s1 3d10 and not 4s2 3d9. Okay. The next we have is the electronic configuration of the heavier elements, where you have to remember about the 4f and the 5d. Okay, so the lanthanides, starting first of all with lanthanum. So the lanthanum, the electronic configuration is going to be xenon, which has atomic number 54. So 54 here, and after that 3 electrons left. So the first 2 electrons, they go into 6s2 because 6s2 is going to have n plus l value less than 5d. Okay, so the next electron has to go into 4f because 4f and 5d, they are going to have same n plus l value, right? But you have to remember that before the filling of the 4f, one electron has to go into 5d, right? So that is why lanthanum, rather than having an electronic configuration of xenon 6s2 4f1, it has the electronic configuration 6s2 5d1, and this is a transition element, as you will learn in the periodic table when we will do the further course. Okay, so this, the electron last is entering into the d orbital and not the f orbital. Next we have a cerium. So cerium has atomic number 58. So here now, after one electron has already gone into 5d, the filling will start in the 4f orbital and it will have one electron in 4f. Similarly, the next element that is going to be having an electronic configuration of 5d1 4f2. Next we have the actinides. So actinium 89. So this is going to have an electronic configuration of Rn, that is radon, 7s261 and not 5f1. Thorium, the next element, this will have the electronic configuration of 7s261 5f1. And the next, that is, we have proactinium, that is going to have 7s261 and 5f2. Beyond Z103, we have atomic number of Z, that is 104. So till 103, it is the filling of the actinide series. You will understand this when we study about the periodic table. But till 103, it is the filling of the last 5f orbital. Okay, so that is the 14th electron going into the 5f14. Next we start with 104 atomic number. So here 5f14 is already complete and the next 9 electrons, they will go into 60. Okay, so for 104 we have 5f14, 62 and 7s2. For 105, it is going to be 5f14, 63 and 7s2. And for Z equal to 106, it is going to be 5f14, 64, 7s2 and so on. Coming up to 112th atomic number. So here we have 5f14, 60, 10 and 7s2 completely filling this all 5f and 60 orbitals. Now some important information again about the electronic configuration of ions. So ions, they are formed by the loss or gain of electrons by a neutral atom. So you have to understand how we write the electronic configuration for them as well. So first we will be talking about cations, which are formed by the loss of electrons from a neutral atom. So again we have iron. So iron, the electronic configuration we have is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 and 4s2. Right? So the last electron, where did it enter? It entered into the d orbital, right? I hope you remember while we were writing the electronic configuration, 4s was filled first and 3d was filled after that. But when we have to remove the electron, well, these electrons, they have gone inside into an inner shell and now they do not want to come out. So what do we do? Well, the electrons, if we have to remove them, the easiest place to remove them is going to be from the valence shell. So when we want to electron to be removed from a neutral atom, this is going to be always from the valence shell and not from the place where the last electron was entered. Okay. So for Fe plus 2, 2 electrons to be lost and those 2 electrons are 4s2. Now if 1 electron has to be lost, this is going to be from 3d6. Okay, so Fe plus 2 loses the valence electrons. Always when a cation is formed, the electron will be lost from the valence shell and not the last electron which entered in. Okay, so I hope you will always remember this. So we have Fe plus 3. This is going to be now 3d5. Similarly, we have zinc. So the electronic configuration for zinc is going to be 3d10 4s2. So here the last electron, this has entered into the d orbital. The 4s was filled earlier, but when it has to lose electrons to form a cation, it is going to be losing these 2 electrons and hence the electronic configuration is going to be 3d10, right? It is not going to be 3d8 4s2. It is going to be 3d10 after the loss of 4s2 electrons. Next we have the anions. Now the anions, the electron is adding up, right? So when it is adding up, it is going to add in the fashion the electron filling by convention takes place. So we have fluorine is 1s2, 2s2, 2p5, and F negative is going to be 1s2, 2s2 and 2p6. Okay, so the last electron, this will enter as according to the AUFBAU principle. Here there is going to be no change. So we have oxygen which is 1s2, 2s2, 2p4. We have O2 negative to be 1s2, 2s2, 2p6, right? The only thing that you have to remember is for the cation that the electron is going to be lost from the valence shell. So the last topic for today's discussion, in fact for the whole of the course, is magnetic character of elements. We are just left with one lecture from this course that would be on the numericals based on the electronic configuration that we've learned in this lecture. Right? So the last topic for today we have is magnetic character of elements, and this is based upon the presence or absence of unpaired electrons in an atom. When the atom, it comprises of unpaired electron or electrons, so this element or ion also, this is going to be called as paramagnetic, right? And what does paramagnetic mean? It means that it can be attracted by the magnetic field. Whenever we apply an external magnetic field, it is going to be attracted towards it. And generally such paramagnetic substances, they are colored. Okay, and then we have elements which are said to be diamagnetic. Diamagnetic means that they are repelled by the magnetic field, and they are going to be those elements in which the atoms, they have no unpaired electrons, and such diamagnetic elements, they are generally colorless, right? So elements which have unpaired electrons, they are paramagnetic. Elements which do not have unpaired electrons, they are called as diamagnetic. And the prediction of the magnetic behavior, this can be accomplished by knowing the total number of unpaired electrons present in an atom. And by seeing the number of unpaired electrons, what are we calculating? We are calculating the spin only magnetic moment, right? So if there are unpaired electrons, that means that the spins of the electrons, they are not completely cancelling. If there were paired electrons, that means the spin of one cancels the spin of the other. So if there are unpaired electrons, it means they have the spin only magnetic moment, and this spin only magnetic moment is called as mu s, and this is given by the formula under root of n into n plus 2 bm. This bm stands for Bohr-Magneton, the unit of magnetic moment, which you will be understanding more while you study the magnetic moment in physics, right? And this n, what does this stand for? Well, this stands for the number of unpaired electron present in the atom. Okay, so higher is the number of the unpaired electrons, higher is going to be the spin only magnetic moment, and hence higher is going to be the total magnetic moment of the element, thus making the element paramagnetic. For example, we have manganese ion Mn plus 2. So if you write the configuration of manganese plus 2, this will come as argon 3d5. 3d5 means it has 5 unpaired electrons, and hence the spin only magnetic moment for manganese ion is going to be under root of 5 into 5 plus 2 bm, coming up to 5.92 bm. Right? So this is how we calculate the magnetic moment for the electrons. The ones which have more magnetic moment, they are going to be paramagnetic. Ones having less of magnetic moment, that are going to be diamagnetic. That would be all for this lecture. So one lecture left for the course to complete. We will be discussing in the next lecture numericals based on the electronic configurations that we've learned in this lecture. If you have any doubts, please mail us at h2ochemistry@gmail.com. You can also put that in the comment section given below the video, and we will be glad to help you. Well, if you've liked the lecture, please do click on the like link. That motivates us to work more for you. And then also do subscribe to our channel H2O and click on the bell icon to get a notification as and when we put up a new course for you, a new lecture for you. So see you again. Bye bye.